Hi, this is Mrs. Cribb, and this is Chapter 4A, the development of the atomic model. So we're going to start off by looking at a Prezi and also at your notes. So you do need to pull out your notes. This is what they look like. Let me get over here. Right there. There you go. This is what they look like for you. Pull them out. You'll need to pull out your targets as well and go along. We're going to be talking about the different models and comparing and contrasting them basically. Okay, so the development of the atomic model, first we had something called the scanning tunneling microscope, STM. It just helps us to see what atoms look like. It doesn't really show you a picture. It kind of goes along the top of it. We may be doing something called a black box experiment where we indirectly try to figure out something, the interior of a box. And this is the same kind of way that they figured out what an atom looked like. I'm going to go back to the Prezi for a moment. And we're going to look at the images for that. Now, first of all, in the Prezi, the Quizlet is there to help you study, the periodic table that you'll need later, and some things that you'll need further on down the road. So we're going to get past all this. And there's another Prezi that's embedded that has a lot of videos that reviews this information that you can look at too. So I may want to, I've referred you to that periodically. So here is the notes inside the Prezi. And this guy right there, there's Democritus. We'll talk about him in a minute, but what I wanted you to see here, a couple of things. One, the video that I'm doing now is embedded right there. And this is the scanning tunneling microscope. This is how it goes across the surface, and it kind of gives you an idea of what the atom looked like. You can see it right there. Okay, now we have Democritus. And Democritus is this Greek guy, and that's Aristotle. They lived around the same time. Democritus believed in something that became the particle theory of matter. He believed particles could not be subdivided infinitely without losing their properties. So think about water, H2O. If you have a whole bunch of water molecules together, you could separate them and keep them as water molecules. But if you keep trying to pull them apart, you're going to end up with just hydrogen and just oxygen. So the particle theory of matter is something that kind of came along after him, but he believed in this idea. He also coined the term atom, and it came from atomos, and that just basically means that we have smallest particles. Now Aristotle, who was kind of won the argument for the day, believed in the continuous theory of matter that states that matter could continuously be subdivided without changing the matter's properties. He thought you could just keep cutting it in half and it would never change, and there'd be no space between those particles. He won for a while, like 2,000 years, and eventually we realized that he was wrong. And next we're not going to go through that, okay, the law of definite composition. The law of definite composition says that every compound is formed of elements combined in specific ratios. Ratios like 2 girls to 1 boy, that's a 2-to-1 ratio. So that's all it's saying, that there's a ratio of masses. That, remember, mass is grams. So here's water, and if every 9 grams of water gives you 8 grams of oxygen and 1 gram of hydrogen, that's the ratio. It's a 9 to 8 to 1 ratio. So I'm going to go back to your notes. Let's fill those in. Okay, so here we are. It's the ratio that we're trying to deal with now. And 9 times 2 is 8. So if I have 9 grams here, if I have 18 grams there, how many grams of oxygen would I have? Well, 8 times 2 is 16, and 1 times 2 is 2. So I'd have 16 grams of oxygen and 2 grams of hydrogen. It's still the same ratio, 9 to 8 to 1. The law of definite composition deals with ratio of masses. If I had 24 grams of oxygen, 8 times 3 gives me 24, so 1 times 3 is 3, and 9 times 3 is 27. It's the same ratio. 27 grams of oxygen comes from 27 grams of water, comes from 24 grams of oxygen and 3 grams of hydrogen. That's a law of definite composition. Now we have the first experimental model, Dalton's atomic model. Dalton around 1803. The atom is an invisible sphere of uniform density. Uniform density. It just means it's the same all the way through. Atoms of the same element have the same mass. So silver atoms all weigh the same. Gold atoms all weigh the same. Lead atoms all weigh the same. have the same mass. And atoms combined in fixed ratios to form compounds. So that's, before we had the mass of the water, but now it's just saying, okay, 2 hydrogens to every 1 oxygen is going to give you your compound. That's a 2-to-1 ratio of atoms, not masses. So the mass of the water was different. It was a 9-to-8-to-1 in mass, grams. This is counting the atoms. So that's what Dalton said. He had this solid sphere. That was his atomic model. And then the next atomic model was from J.J. Thomson. He was a scientist that discovered cathode rays, which were emissions from a cathode, a negative electrode. The cathode is the negative electrode. And so we have this negative electrode, basically, this negative source, and it's shooting out these particles. Okay? Now, he set up some plates, and this plate was positively charged, and this plate was negatively charged. And he shot these little particles, and they bent towards the positive charge. Well, why would these little particles that he shot out, these little little rays that he shot out, why would they bend towards the positive side? Well, it's because opposites attract. And that's something that's super important to remember. Opposites attract. And that in chemistry, a lot of what we do is going to be dependent upon that. So these little particles that were shooting out bent toward the positive plate, so they must be negative. These cathode rays became known as electrons. So now we had to change our model, because before we had this solid sphere up here, but now we realize that things shot out of it, and the things that shot out of it were these little negative bits. And these little negative bits were inside the atom then. So we had a positive goop, all this stuff around these negative bits. Think of it as like Jello almost. Okay, it's not really, but it was kind of like that. All this stuff was positive, and then we had these little negative bits inside of them. It was called the plum pudding model. I call it the chocolate chip cookie model, but plum pudding model is the one that you need to remember. I'm going to go now back to the Prezi and show you a video about how he discovered this. So let me get to that.
So today I'm at the University of Sydney with Dr. Phil Dooley, and we're talking about how our idea of the atom changed from a tiny little hard sphere to something more complicated. And this apparatus has something to do with that.
Exactly. It was quite a landmark historical experiment. It's just made of a tube of glass connected to a vacuum pump, and in the tube of glass there are 2 pieces of metal connected to a high voltage power supply.
So we can suck the air out of here.
That's right.
And then apply high voltage to 2 metal plates.
Okay, so they're going to apply voltage. This is the cathode. The cathode is the negative plate. It's going to send the little bits out of it. It's going to send the little negative bits out of it. They're going to be attracted to the anode, which is the positive plate.
Okay. Normally with high voltage in air, we don't get anything except maybe a big spark. But what Geissler found, who did this in 1857, was something quite different. So should we have a look?
Let's do it.
Okay, let's turn on the pump and the high volts. Turn off the lights so we can see what's going on. As you can see, something's happening now.
Yeah, I see a bit of a pink glow in there.
That's right. So imagine Geissler, the first person to ever see this. It's pretty surprising. That started people thinking, what is this stuff that's coming from the cathode? It seemed to be a ray emitted from this negatively charged one, which they called the cathodes, therefore it's called a cathode ray, and it became the topic for research for the next 40 years as all the big wigs of physics and science basically tried to work out what was going on.
So what did they figure out? I mean, what is going on? What's producing this this glow here?
There were 2 main camps. One thought that it was waves, and the second thought that the electricity was being carried by a stream of charged particles. Over the next 40 years, they basically came to the conclusion, well, it was J.J. Thomson in 1897 who came up with the idea that there is a stream of very small charged particles, negatively charged. They're smaller than an atom. So the smallest atom, hydrogen atom, they're about 1,000th of the size of that. And it doesn't matter what material the metal is, it's always the same particle. So this particle appears to be in everything. Yeah, this electron, as it was known, is what's carrying the electricity.
So Thomson came to the conclusion that all atoms have this particle as one of their constituents.
Okay, so you can see that's how they came about, working on the changing the atom into something else. Okay, so into a new model. So now Thomson's model was improving because we just discovered electrons. We discovered the atom wasn't solid. Now we have to go on to Rutherford's model, the nuclear model that has and then it ends up having protons in it and later neutrons. But Ernest Rutherford discovered protons. Notice the time frame that we're dealing with now, 1937, right before, that's when he lived, right before World War II. And so he had these things called alpha particles. Now this is the alpha particle right here. Okay, it's an alpha particle has 2 positive protons and 2 neutrons, and we didn't know that was. And it's basically the center of a helium atom, because a helium atom has 2 protons, and let's write it this way: 2 protons, 2 neutrons, and it has 2 electrons orbiting it. All right. That's what we know now. And if we got rid of those 2 electrons, this is helium, by the way. This is just helium. Oh, I've got it on eraser. There we go. This is just helium. But if I get rid of these electrons, then we have just the center of the helium. And what we have left is, well, what we have left are those 2 protons and those 2 neutrons. That thing right there, the alpha particle. So it's the nucleus of a helium atom. So he shot these alpha particles at some gold foil. I have a picture of it right here. And Hans Geiger, who's one of his assistants in his Geiger counter fame, to count radiation, he designed the gold foil experiment. So they had this thing that's going to shoot out these alpha particles. I'm just going to make it little A's. I'm shooting out these A's at this plate. Now they thought at this time that we were still dealing with the plum pudding model. They thought that atoms were still solid, but they had little bits in them. Okay? And they expected these alpha particles to go straight through because it wasn't very massive. But instead of going straight through, now alpha particles have positive protons and neutrons in them, so the charge of this whole alpha particle is a big positive. Okay? So this is a heavy positive. All right, went, and a lot of them did go straight through, and they hit the back of the screen and they lit up. Every time it hit, it lit up. But some of them deflected over here, and some of them actually deflected way over here, and some of them actually went straight back. So they didn't always go straight through. They were expecting them to go through. It's like throwing a tennis ball through tissue paper. They didn't expect the tissue paper to shoot the tennis ball back at you. They expected it to go straight through. Well, it didn't. It did something weird. And so they thought, well, why is that happening? Well, the only way for that to happen is that the atom couldn't be this big thing with just little bits of particles here. There had to be a concentrated center that's positively charged. And so the electrons had to be going around it. So there's a lot of empty space in the atom then. All this area between the center and the electrons are empty, and those alpha particles could shoot go straight through it, through that empty space. And the only time they wouldn't is if they hit the nucleus. They would bounce back because the alpha particles were positive, the nucleus was positive. And so remember, opposites attract, but what do likes do? Well, this is because likes repel. Opposites attract and likes repel. So since likes repel, when the positive hit the positive, it bounced away from it. Just like when you put a north and a north side of a magnet together, they push away from each other. Most of them went straight through the empty space of the atom. But some of them bounced away because of the concentrated positive center of the atom. And so you shoot a positive thing at a positive thing, and they deflect it away. So this is how Rutherford reasoned that there must be a positive center of that atom and came up with the term protons. So Rutherford figured out protons. And now protons, the atomic number of an atom is the number of protons. That's very important. The atomic number of an atom is the number of protons in the nucleus of the atom. Okay, I'm going to go back now to the Prezi and watch a very short video about that. So here's that cathode ray. By the way, there's a positive and the negative plate. You send those negative things out and they shot towards the positive, so we knew that they had to be negative. So that's where we changed the Thomson's plum pudding model. Now let's watch this video about Rutherford's experiment.
In 1910, Rutherford and his co-workers were studying the angles at which alpha particles were scattered as they passed through a thin gold foil.
Now notice all the lighting
Most of
up.
the alpha particles passed through undeflected. However, a few were found to be scattered at large angles, some even back in the direction from which they had come. This meant that they had collided with an object much more massive than the alpha particles themselves.
Now look at this for a minute. This is a plate they put around it, and that plate was set up so that it would detect the particles as it hit. So here you see the particle just hit, so it lit up. Okay? And then whenever you see the light show up in other places, that's because the particles bounced back. Those alpha particles bounced back.
Yet so small that only a few alpha particles encountered them. This atomic level view shows what is happening. All
right, now I'm stopping it again. There's that nucleus that was actually there that they didn't know about until this. Most of the particles went straight through all that empty space between the electrons and the nucleus. But when they got close to the actual nucleus, that's when they bounced away.
The atom is occupied by the low mass electrons. The nucleus is small.
So if it hit there, it bounced away. Watch that.
And massive. When an alpha particle encounters a nucleus, it is scattered at a large angle.
Okay, that's how they figured it out. So that's a gold foil experiment. That's important for you to know. Okay, so that brings us to this part of our notes, the discovery of the neutron by Chadwick. All right, there's Chadwick. In 1932, James Chadwick discovered neutrons. Basically, what happened was they could add up the mass of the proton and electron, and that wasn't, the atom was heavier than that. So they knew there had to be something else there, and so they figured out where neutrons were in the nucleus of an atom. Okay, I'm not going to worry about any more detail than that. So this was Rutherford's model before we figured out there were neutrons. We just knew there was a positive center, the nucleus, and we knew the electrons were going around it. And this was the model after we figured out there were neutrons. So we have protons and neutrons in the atom at that point. Okay, now when you have that, now we know about these particles, electrons, protons, and neutrons. Electrons are negatively charged, and this is the mass, 9.11 times 10 to the minus 11 kilograms. Protons are positive, and they both start with P, and there's its mass, times 10 to the minus 27, so it's a little bit larger. And neutrons have no charge, and neutrons are neutral with no charge, all start with N's. It also has 10 to the minus 27, but do you see this number right here, this one tiny little number? Shows you that the neutron is just slightly larger than the proton. So if you put them in order, neutrons are the heaviest, electrons are the lightest. Notice electrons orbit the nucleus, and the nucleus contains the protons and the neutrons. Now we are going to add one more thing that's not in your notes, so you need to add this in and write it. We're going to talk about quarks.
What are quarks? Over the past century, discoveries in physics have come thick and fast. Some have changed the way that we understand the world. An understanding of the structure of the atom has been a huge focus of scientific research, and it has heralded an era of discovery unlike any we have ever seen before. In 1964, Murray Gell-Mann and George Zweig suggested that most of the known particles of the time could be explained as being combinations of three fundamental particles. Now, the term fundamental means that the particle does not have a substructure. It cannot be split. The name quarks was chosen from the James Joyce novel Finnegan's Wake. 3 quarks for Muster Mark. In order for their calculations to work, however, these quarks needed to have a fractional charge. This was a new concept, as fractional charges had never been seen before. Quarks are the fundamental building blocks of all particles that we know of. At the Stanford Linear Accelerator, electrons were fired at protons and found to bounce off of tiny particles inside them. It had taken 4 years, but this was the first evidence for the existence of quarks. At the time, there were 2 basic quarks, the up quark, which has a charge of plus 2/3 of the charge of an electron, and the down quark, which has a charge of minus 1/3.
Okay, so these are the quarks you're going to have to know. The up quark has a plus 2/3 charge. Write that in your notes. And the down quark has a minus 1/3 charge. Write that in your notes. If you want to make them happy and sad, that's probably a good idea too. And now we have to figure out what the proton is made out of.
How are they different? They all have different masses, as well as charge, and another property called spin. The up and the down quarks are the most common and least massive. The proton.
Okay, so I'm going to go on from there and just show you another picture that shows the relative amount. So there's a proton. A proton is made up of two up quarks. Remember, the up quark has a plus 2/3 charge, and one down quark, which has a minus 1/3 charge. So plus 2/3 is plus 4/3, and take off 1/3, that gives you a plus 1 charge. The neutron is made out of an up quark, which is a plus 2/3 charge, and two down quarks, minus 1/3, minus 1/3. So that's added together, you get neutral charge. That's what I want you to know. I want you to add this to your notes. Protons have two up quarks and a down quark. Neutrons have one up quark and two down quarks. And that's as far as we're going to go with that. Now the next model we come to is Bohr's model, planetary model of an atom. So Niels Bohr worked in Rutherford's lab. A lot of people worked in Rutherford's lab. Okay, he used spectroscopy, the analysis of light emitted or absorbed by matter, to develop the idea of principal energy levels. And there's a thing you can do jumping up and down stairs that we might be able to do with this. There's things you need to know though. The continuous spectrum, what happens when light passes through a prism, that's like the rainbow. Aligned spectra, what happens when electrons fall from a higher energy level to a lower level and emit a photon of light. All elements have their own line spectra. It's like the fingerprint of the element. And the principal energy levels are levels in which the electrons orbit the nucleus. Now I'm going to show you some pictures about all this. Electrons want to orbit in the lowest energy level possible because nature is lazy. And when all the electrons are in the lowest energy level that they can occupy, that's called the ground state. Think about standing on the ground and jumping up and down the stairs. So when you're on the ground state, that's the lowest energy level. And when you jump up to a step, you've gone to a higher level. You had to bend your knees and jump. You took in more energy to get there. So the lowest level is the ground state. Electrons can jump only from one level to another. Think about going up and down stairs again. You can't jump up to stair 2.5. You can jump up to stair 2 or 1, but not 2.5. So they have to jump up to one certain level. And this jumping requires absorbing or releasing a certain quantity of energy. When you bend your knees, you absorb some energy and you push, and then you release that energy basically when you fall back down. Released quantities of energy are called photons, and they are massless light particles, and they have a certain wavelength of light depending on how far they are from the nucleus. Okay, let's look at a few pictures. This is that rainbow, the continuous spectrum. These are emission lines. So this is when when an electron basically falls down and lets go of extra energy, it lets go of this energy. And that energy has a wavelength, and that wavelength shows up with these colors. And the bottom, these are absorption lines. So this is the energy the electron had to suck up before it jumped. I'm going to show you some animation on this that will make this even more clear to you. So here we have energy level 1, energy level 2, energy level 3. The ground state is the lowest energy level. Okay? And these are called excited states. Now here's my little electron, and it's got its normal amount of energy. Now it's going to suck in some energy. Here HB stands for the energy. That energy is going to come in, and an electron is going to suck it up. In this case, it looks like it's sucking up red wavelength. And now it's going to give it just enough energy to jump. So it jumps up to the second level. So now it went from energy level 1 to energy level 2 really quickly. It didn't jump up halfway and stop. So that's an excited electron with too much energy. Nature's lazy. It's unstable. It wants to go back down to being lazy. So now it's going to fall back down to where it came from, back down to the ground state. And it's going to let go of that extra energy. That's the photon of light. And your little eye can watch that light and you can see it as that red color. There he goes. Oh, I see red. That red color comes from that extra energy that came out of that electron. So let's do one more time. We're going to give it even more energy. So again, here's the ground state. There's my lazy electron. It doesn't have extra energy. Here comes a purple or violet color of energy, violet light energy. It's going to suck it up. And when it sucks it up, it jumps up to the third energy level. It didn't jump to the second. It could jump all the way straight to the third level. Let's jump from the ground to the third step. Now it's an excited electron, unstable. It wants to be lazy. It wants to go back down to the ground. So it falls back down to the ground and it lets go of that purple light. That purple light is a photon of light, and it travels in a little package that we call a photon, and it's a wavelength as well. So that's the principal energy levels. They could just observe those line spectra and be able to see. So again, let's look at this. Here we have an electron, and it's going to suck up some energy. So here's the electron, sucks up some energy to go way up here. And so it sucked it up, and this is the energy it's sucking up. And so if you have the continuous spectrum, you can see which one, what energy it took. And when it falls back down, that's the energy it lets go of. This one right here, the electron, in order to get to here, had to suck up this blue energy. And when it falls back down, it lets go of the blue energy to create that line. This is the line spectra for what's going on in that element. You know, every atom has its own line spectra, and that's like the fingerprint. So this is what hydrogen looks like, what helium looks like, what argon looks like. And if you look at the pictures, you can tell what element you have by what colors of light are being emitted from the element. So this picture also helps depict that. We have energy coming in, it jumps up to be excited. If it was excited and it falls down, it lets go of it. It lets go of the photon. It only can go to certain levels, certain quantities of light, and that's where we get the principal energy levels. And that's when we started to get Bohr's model of the atom. Okay, before we go on to the quantum model, I'm going to go back to your notes for a second. All right, so here we have that. There's Chadwick's model and Rutherford's model. And we talked about the relative sizes of the particles, and we added quarks. And so you should have added in here that a proton, it has 2 up quarks and 1 down quark. And a neutron has 1 up quark and 2 down quarks. And the up quark has a positive 2/3 charge, and the down quark has a negative 1/3 charge. Okay, so you need to make sure you added that in there. And we talked about this, and this is the picture, and notice you can go to the atom model changes, Prezi, to see all this. And that brings us now to the quantum model. Now the honor students, you're going to have additional notes on de Broglie's equation, which we will talk about later. Now quantum model, electrons act as a wave and a particle. So everybody has to know this general information. Electrons, and we saw that here. Look at these guys. This is a photon of light, and a photon acts like a wave and a particle. Electrons act like waves and particles. De Broglie's hypothesis, if waves can behave like particles, then particles could behave like waves. Whether an object acts like a particle or wave depends on how we look at that object. So all forms of matter act like waves. Students and baseballs, we all act like waves and we all act like particles. That was the de Broglie's hypothesis. Okay, now orbitals describe the path of electrons around the nucleus of an atom. Okay, and they're more like probabilities. So we're talking now about orbitals. Okay, because we're talking about the quantum model. So up here, where we had Niels Bohr, we had principal energy levels, and those were like orbits. The principal energy levels are like orbits, like the planets orbiting the sun being the nucleus. But now we don't have orbits, we have orbitals. So that's different between Bohr's model and the quantum model. The quantum model is the most modern model, but we use Bohr's model a lot. And I'm going to show you some more pictures of those two. And there are some more pictures in the addendum to these notes. But orbitals act like probabilities. And then we have something called the Heisenberg uncertainty principle. It is impossible to know both the energy or momentum and the exact position of an electron at the same time. When you try to figure out where an electron is, you hit it with something. Well, when you hit it, you've changed the direction it was going and you changed its speed. So you can't know both. This is the Heisenberg uncertainty principle. I'm going to go back to my Prezi for a moment so we can pull this up and look. So this is a quantum model. You can see the energy levels. That's energy level 1 right there. And that's energy level 2. And then we have these are orbitals, p orbitals and s orbitals, or the circles, the spheres for s, p. We're going to go through these shapes and talk about them in detail a little bit later. I also wanted to show you the probabilities. So the Heisenberg uncertainty principle and the high probabilities. So this is the probability cloud, electron cloud or probability cloud. The nucleus is down here. Now we have all these little random dots going around here. That's where the electron could possibly be. We don't know for sure. The darker it is, the more likely the electron is there. So the higher the probability it is. So that would be energy level 1 and that would be energy level 2. But the electron could also be somewhere in between. So it's not just like the orbits of the planets. It could be anywhere between the sun and poor old Pluto that's no longer considered a planet. It could be anywhere in there. That's the probability cloud or the electron cloud of the quantum model. Okay, the Heisenberg uncertainty principle, I told you they don't know where it is. And you know, I'm a huge Star Trek fan. So if you watch Star Trek in the show, they talk about the Heisenberg compensator. And that's what it's there for. Because the Heisenberg compensator compensates for the fact that we really don't know where those electrons are. So when they take the people apart in the transporter, they got to be able to put them back together, and something has to figure out how, and that's what that Heisenberg compensator is for. So yeah, that's not going to happen. All right, so that brings us to the last picture in this first section, just a review of the different models. This solid sphere, which was the original one, plum pudding or chocolate chip cookie model with the little bits of negative electrons surrounded by positive goop. Rutherford's atomic model or nuclear model with the nucleus and the electrons going around it rather. Bohr's model. Now remember, after Rutherford we added the neutrons in there from Chadwick. Bohr's model, which has the orbiting electrons around the nucleus, like the planets orbiting the sun, they have orbits and energy levels. And the quantum model, which is electron clouds, probability clouds. And it's what is the most used now. So we're going to go back to our notes for just a moment to see if there's anything we need to add. I think that's it. And that's the end of this first chapter. I will hopefully see you soon.